Okay, so welcome to this video. So in the last lecture we have seen how to define the placement problem in general, and right, so apart from that we have also discussed the various models of wavelength estimations. Now we discussed that why wavelength estimation is required to define the placement problem, and what is the main objective of placement in phase of physical design cycle. Right now in this video we are going to discuss primarily two algorithms to solve the placement. In the first part of the video I will going to discuss one algorithm that is for the standard cell based design, one algorithm in placement algorithm for standard cell based design, and another algorithm for full custom design in the second part of this video. Okay. Now we know that the placement is the process of arranging the circuit on a layout surface. The process of placement consists of finding the optimum physical locations for the VLSI blocks or cells on the given layout area. If we are provided with the dimension of the cells, the collection of the nets joining them, and the input-output ports on the boundary. The optimum locations means that they minimize the given objective function according to some constraints. Now objective function usually is the total wavelength, okay, and while the constraint can be avoidance of overlap of blocks or cells and maximum chip area size, etc. Now placement problem in general sense is a NP complete problem. Now if the number of blocks involved is small, suppose let's say 10, then it is possible to enumerate all the possible solution to the placement problem and you can pick an optimum one. But for large problems, means the number of blocks are quite large, then the solution space is too large to permit the enumerative techniques. Okay. Now it is therefore natural to turn towards heuristic techniques which require short execution times and find some good solutions, if not the best solutions. Okay. Now let me discuss a few things regarding the design style specific issues. Okay. Now let's for full custom design style. First one is a full custom design style. I think this does not require any further discussion because in the last video we have mainly defined the placement problem in the context of full custom design style, where in the placement phase our task would be to place the blocks of various shapes and sizes within a rectangular region, and we keep adequate empty regions or spaces for routing, right? Means so that we are keeping some adequate empty space between the cells or between the blocks, okay, so that we can basically lay out the wires for interconnections, right? Now in the full custom design, the entire silicon area is your design floor actually. Now for standard cell design, but for the standard cell design we know that this placement problem is somewhat different. Why? Because in standard cell, unlike full custom design style, in standard cell based design, the layout area is divided into several rows, right? And a row consists of cells placed next to each other. Okay. And since we know that all the cells are pre-designed to have the same height, the height of a row is the same as the height of any cell in the row. Okay, right? So here is an instance of full custom design. Now what are the routing options? What are the options for routing in full custom design? Okay. Now what are the options for routing in in the standard cell based design? Now in standard cell based designs, the rows are separated by some horizontal routing channels. Okay. So channels means the space between the cell rows. Such regions are called a channel. Okay. And cells within the same row or cells from the two facing rows, means two adjacent rows, can be interconnected by running wires through the adjacent channel. Okay. So routing between standard cell rows uses either the available routing tracks between the rows or some feed through cells within within the rows. Now you already know, we already discussed what is a feed through cell, right? So it is nothing else but a nothing else but a one or more vertical wells running straight. So feed through cell is used when we have to connect two cells which are in non-adjacent rows, right? So here is an examples of a standard cell layout with net A and A with net A dash routed through a feed through cells. You can observe over here. Okay, so here you can see that this net A dash routed through a feed through cell, and cell rows separated by channels, and each row has its own power and ground rails. Okay, now basically in standard cell based design, the routing options are basically the channels, that we already defined, that the channels are spaced between the cell rows, and such regions are called the channels. Second option is the feed through cells. Okay, those special type of cells which is nothing but one or more vertical wells running straight, so that we can interconnect the non-adjacent non-adjacent cells. Okay, and another technique of routing also there, that is called, which is quite prevalent in modern process technology in VLSI, it is called the over the cell routing, or OTC. Okay, now OTC has become somewhat popular as a way to use multiple metal layers, usually more than 3 layers in routing phase, and usually right. And in OTC, what we do is the space above the cells can be utilized for routing. Okay, now and this routing style, this OTC routing style, is more flexible than traditional channel routing. And if OTC routing is used, then adjacent standard cell rows are typically not separated by routing channels, but instead they share either a power rail or a ground rail. Okay, and OTC routing is quite relevant in the industry today. Now here is an instance of standard cell layout, where you can see that there we are using the OTC routing, and you can observe that this same net A dash is routed using the over the cell routing. Okay, and so cell rows share some power and ground rails. Okay, so you can see that the OTC, when we are using OTC routing, we don't actually use any space. We don't actually use any this channels. The space between the cell rows are very, very narrow. Okay, and only this narrow region is used to we keep this narrow channel region, we keep this space because for power and ground routing, and we just run the power and ground rail. Now okay, so this is the, so for OTC routing, that means it's kind of a special scenario where we can have some very narrow channels. So it is kind of a channelless standard cell design, where the routing is done through mainly over the cell routing, using the technology called over the cell routing. Okay, and over the cell routing is designs with more than 3 metal layers. During the routing, use the over the cell routing, or OTC routing. Okay, now let me get back to the point, that means the placement problem, which deals with the minimization of the layout area. Okay, so you can understand, so in the standard cell based design, the placement, standard cell based design placement has less freedom, right? So in the context of standard cell based design approach, the objective of placement would be to minimize the height of the channel region. Okay, so usually it is desirable in the standard cell based design, so we have to minimize the sum of all the channel heights, means all the spaces between the rows. Okay, so we have to minimize the sum of all the channel heights, and our target would be to also, it is desirable in standard cell based design that widths of all the rows should be more or less equal. Okay, so also we have to minimize the placement also takes care of minimizing the width of the widest row. Okay, and over the cell routing is a special kind of routing technique where and that is very when it is used, special case, and when it is used it's like you are not using any the channel region becomes very narrow, and we don't use that channel region to for we don't use for routing, rather only we use that we keep this space, this narrow channel space region for power and ground routing, and running the we run the power and ground rail basically. Now we can observe the same thing over here. Okay, so here for when you are using OTC, there is no routing, means normal wires for interconnecting the rows or interconnecting the cells, but we only using this routing channel region for running the power and the ground rail. Okay. So this is some issues regarding the design style specific issues regarding the placement and routing. Now now I'm going to discuss the algorithms. The first one is the TimberWolf package, software package for placement, and which is particularly used for standard cell-based design. Okay, and another method, the second one, is called the force-directed placement algorithm, which basically considers a mechanical analogy of mass spring system. We'll look at this, and it is kind of a general approach, and we can apply it to full custom design also. Okay. Now let's get to the point that what is TimberWolf. Okay, what is TimberWolf? TimberWolf is it's just a software package written in C programming language, and it is academically developed by Seinchen and the Sangiovanni Vincentelli in UC Berkeley. And initially it was developed academically, and then it is commercialized and incorporated in VLSI CAD tools. Okay. Now it is based on basically the simulated annealing algorithm, which is a probabilistic iterative improvement technique that you already know, and you know that simulated annealing is a general algorithm for solving the combinatorial optimization problem. And the salient feature of the simulated annealing is that it has some provision of accepting the inferior solutions in hope that it will get out of local minimas. So TimberWolf is a standard cell, basically TimberWolf is a standard cell placement and routing tool. It places the cells such that the total estimated interconnect cost is minimized. So in this stage, the TimberWolf uses a modified version of normal simulated annealing algorithm with certain constraint and restriction on the cost functions and cooling schedule. And after that, the tool routes the placed cells and tweaks them for the area optimization. Okay, and we are going to focus on the placement part of it. So TimberWolf package handles standard cell circuit configuration in which the standard cells are arranged in horizontal rows. Now let's discuss some of the important details of TimberWolf. Okay, so what we're trying to look at now, we're trying to look at how simulated annealing can be used to solve the placement problem, right? Now again, the placement problem is a combinatorial optimization problem, where our objective is to minimize the total wire length, and we know to compute this wire length when we have a set of blocks with a defined pin location and a net list, and we know how to estimate the wire length of 2-pin net and multi-terminal net. We have discussed different kinds of models in the last lecture, right? The RMST model, RSMT model, and RSMT and half perimeter wire length model. Okay, so we can use any kind of model, and we can sum up all the lengths of all the nets, and we can define a cost function. Okay, now we'll look at that in TimberWolf. When we are going to define the cost function, it also considers the other constraints like overlap of the cells and the row length inequality length, because that is also that needs to be penalized, because the slope of the overlap of cells and the row inequality, both the row length inequality both has to be penalized, and those are some constraint of this placement problem for standard cell based design, right? So another thing that is important, so we are going to look at the cost function, how to define the cost function in TimberWolf, and how to define the now one part of the cost function you already understood, that that has to be the total wavelength estimation, okay, and another part will be the part of functions. Now next thing is the part of function. Now in similarity annealing, the local is basically a local search based algorithm, right? So starting from a random initialization, we search around the current solution, and or we can say it is a current state. We search around the current state, and then we make some changes make some variation in the current state, and we compute a new state. So we need to define some part of function which will will generate a new placement solution from an existing placement. Okay, so we look at some of the perturbation techniques. Okay, so that perturbing function, so that we can find a new placement by perturbing the current placement. Okay, so these two are the very general technique that you already understood in fold planning. Also we had some perturb functions, and right in the partitioning we had some part of function for similarity. And similarly here we are using this TimberWolf, which is also a placement, which is as a simultaneous annealing based placement algorithm. Also we have to define these two functions, how to calculate the cost function, how to calculate the part of functions, right? Now let's see what is the part of functions. Okay, now before going into that, let's see the composite form of this algorithm. So as you already understood what should be the similarity annealing based placement algorithm, so it is just the pseudo code of this algorithm. So we'll start from an initial temperature, and then we'll define the initial placement, that will be randomly selected a state or a configuration, particular configuration. Then we'll run the two while loop. First while loop will terminate based on the final temperature condition, or T minimum, whatever you will put into the algorithm. And the second while loop will impose some kind of a restriction, the number of trials. So we will impose some termination condition we will going to impose. Usually it is number of trials at each temperature. Okay, and based on that we'll find out some new placement solution by using the part of functions. Then we calculate the cost function of the new placement solution, and also the cost function of the present cost function of the current solution or current placement. And then we calculate how much, if we consider the if we take the new solution, then how much cost variation is there, or the cost is decreasing or increasing. And based on that, since it's a minimization problem, so if it is delta C is less than 0, then obviously we have to accept the new solution, so then the newly generated solution, right? So P will be equal to new P. And even it is not a good solution, so if delta C is greater than 0, then also there would be some finite probability, that although that probability is very less, but there will be some finite probability of accepting that newly generated placement solution, in hope that it will get out of the local minima if it gets stuck at a local minimum. Okay, now now then there is a schedule function we have to define, where we will going to decrease the temperature. Okay, and then again this loop will iteratively so this thing will iteratively going to find the solution until the T is greater than the T minimum, or the final temperature, whatever we are going to define in the algorithm. Okay, now now let's see what is the part of function in case of TimberWolf. Okay, so part of function generates a new placement from an existing placement using one of the following actions. So we basically will select, we are going to select any of this usually the first two actions, the move and swap actions, randomly. Okay, and if the first and second move is not feasible, then we go for this third action, that is called mirror action. Okay, now let's see what is move action. The first action is that in a move action, what we'll do, we randomly choose a cell, okay, and we send it to a new location, or a new location means to a new row, okay, new position, okay, and that would be another row, okay. And in the swap, what we do, we exchange two cells. We randomly select two cells, and we are going to we will exchange their positions. Okay, so this two are the move and swap is these two is a function part of this function. Now this third action, that is this mirror actions, actually used only when this move and the swap are infeasible. Okay, so what is the mirror option? We actually reflect the cell orientation around the y-axis. Okay, so it means you randomly select a block or select a cell, and you will flip it in y direction, or in other words, you will going to take the mirror image of the block, okay, across the y-axis. Okay, so what will happen in that case also, if we take this kind of action, though it may happen that the pin location of the black may change, but its position will remain same. Okay. So part of function select the third action that is this mirror actions, only when the action 1, this move and this swap are infeasible. Okay. Now there is another feature of important feature of TimberWolf is the range limiter function. Okay, now which actually modulates the scope of the part of functions. Okay, now let's see what is this. So this action is also being motivated. Now this range limiter actions, or the modulation of this part of function, modulation of the scope of the part of function, is being motivated by the physical annealing process, where we know that at high temperature the atoms of the metal move around from any location to any other locations. Okay, and then so there is quite a high mobility is there, and then they settle down finally. So initially there is this type of volatility is observed. This type of volatility at high temperature is observed, but then as the temperature cools down, then when the cooling down occurs, most of the atoms get settled down, and there would be very less movement of the atoms, right? Now in TimberWolf, and this type of feature is incorporated by introducing a window of width WT and height HT. So we are going to define a region. We are going to define a rectangular region in this in this total chip area, and where the scope of part is limited to a small window size of WT into the HT. And for move, a cell can only be moved within this window. Okay, and for swap, two cells A and B can be exchanged only if they are within this bounded region, within this defined rectangular region. Okay, now this window size, this size of the window is not constant. Now that's why we are calling this as WT in HT, and this T is in the suffix, right? So the size of the window is a function of parameter T, or temperature parameter. So at the beginning, this rectangular region, okay, which is defined by this WT and HT, the height and the width of this region, which is basically very large, big enough to contain the whole chip area. Okay, so initially we'll consider the whole chip area, but then what we're going to do with the index size, it's going to shrink slowly as the temperature decreases. Okay, so we'll see that this WT and HT, okay, so this window size WT HT depends on the current temperature, and it decreases as temperature reduces. Okay, So window size for the next iteration is based on the current temperature T current and the next iteration uh, next iteration temperature. Okay, so T next. Okay, so using this type of logarithmic functions, we are going to modulate. We are going to change the size of this window. Okay. So you can understand. So in the TimberWolf, basically impose some kind of limitation on the scope of the Porter function, which leads to be useful for finding out an optimum solution or near optimum solution quickly. Okay, so it means that when the temperature is high, means when the T parameters value is very high, there is a high mobility of exchanging. So this move and swap can explore more solutions. Okay, but when the temperature is decreasing, by changing the size of the window, we are actually imposing some kind of a limitation on the solution variation. Okay, so basically we are modulating the scope of this part of functions, where it is kind of a range limiter. It is kind of a limiting its variability. Okay. now now let's see what are the components of the cost functions. What are the different components of the cost function? Now this composite cost function consists of three individual cost. Okay, first is the cost 1, then we have cost 2, then we have cost 3. Okay, now what is the cost 1? The cost 1 corresponded to the weighted sum of estimated length of all nets. Okay, cost 2 corresponded to the penalty cost for overlapping. So it takes into account the amount of overlap. What is if any overlap happens during the perturbation, it will take care of it, the cost 2. And cost 3 is the penalty cost for uneven length among standard cell rows. So basically it takes into its cost 3 corresponding to the row inequality length. Okay. Now what is cost 1? Okay, now what is cost 1? Or this gamma 1. So now I'm introducing some mathematical notation. So gamma is basically gamma 1 plus gamma 2 plus gamma 3. Now first gamma 1 is the cost 1. Okay, now what is cost 1? Cost 1 is computed as the summation of each net's HPWLs. Means HPWL means the half parameter well length model. So a well length of each net is computed by using the HPWL model. Okay, which is so it's particularly I'm talking about the TimberWolf. Okay, so particularly it is whatever there in the TimberWolf package that I'm discussing. So this gamma 1 is basically computed as the summation of each net's HPWL or half perimeter well length, which is basically its horizontal span plus its vertical span. So when we are going to compute the HPWL, we have to consider the horizontal span and the vertical span, and we are going to consider both the things. And in addition, we are going to apply some kind of weight for each direction. So here you can see this is the horizontal span, this is the vertical span of a net, and we are going to apply some kind of a weight for each direction. Okay, this is the horizontal directions, horizontal length, and this is the vertical length. So we're going to impose some kind of a weight for each direction, the horizontal weight WH and the vertical weight WE, right? Now there is another term that is called the small gamma 1, and this is basically the priority. This gamma 1 is basically the priority weight of cost 1. So, and this small gamma 1, gamma 2, gamma 3 will be there for all the cost functions, because this is basically priority of a particular cost. There are three cost 1, cost 2, 3. This is a kind of a priority weight that we are going to use. Now what is the significance? Now next question, what is the significance of giving two different weights? So giving two different weights that for on the horizontal span and the vertical span of HPWL. Okay, so a higher weight value for a net gives higher emphasis on reducing its net's wear length basically, right? A higher weight value for a of a net gives higher emphasis on reducing net's wear length. Okay, and weights can also use some direction control and giving preference to a certain wearing direction. Okay, so that's the main reason. And we know during the standard cell placement where the feed through cells are limited, so low horizontal weights encourage the usage of horizontal channels rather than the vertical canals, because this feed through cells are very limited, so we cannot use always the feed through cells. So to minimize the number of feed through cells, we have to impose uh, low horizontal weights. So we have to actually use low horizontal weights, and that will encourage the use of horizontal channels rather than the vertical connections. Okay, so that is the main reasons of imposing or applying some kind of different weights for each direction, the horizontal weight and the vertical weight, or horizontal weight on the horizontal span and the vertical weight on the vertical span. Okay. Now next is the cos 2 or gamma 2, capital gamma 2. Now represent basically the total cell overlap of the placement. Okay. Now let this OIJ is basically represent the area of overlap between the cells and IJ. So this gamma 2 is defined as the sum of square of the all cell overlaps between the cells I and J, and this I and J are basically part of the a set of cells, okay, so which are being considered for the placement. Okay, so this gamma 2 is again the priority weight of the cost, overall cost 2 in the total cost. Okay, so as you know, this overlapping in placement is undesirable. Okay, and larger overlap which require more effort to correct are penalized more heavily due to this quadratic form. Means we are using some kind of a quadratic functions to define the gamma 2 or the cos 2, and it is basically when this cost function, this overlapping is quite large. So for large overlaps, it is we are going to impose some large value, and it is being penalized by more heavily due to this quadratic form. So we are taking the square form and it will going to penalize it. So it is quite undesirable. That would be actually reflected through this reflected by taking the square form. Okay, so that's why this quadratic function is used to define the cos 2, and it is basically takes care of that how you can how you penalty cost are you are going to consider for overlapping. Okay. Now now another thing is cos 3, the third cost of the overall composite cost of TimberWolf. Now what is the cos 3? The cos 3 or gamma 3, capital gamma 3, represents the cost of all row lengths, L row, that deviate from the predefined some maximum length or optimum length that we are going to put for your algorithm. That is that what would be my optimal length for a particular, and that depends on the size of the chip that you are going to use. Okay, so the total silicon area. Okay, so that also depends on your design. Okay, so you are going to define this L optimal of a row from we will predefine these things in the algorithm. So this gamma 3 will basically represent the cost of all row lengths, L row, that deviate from the predefined maximum length or optimum length during the placement. Now as discussed, when we will apply the Barter function, the cell movement can often lead to some row length variations, okay, and where the resulting rows lengths deviate from the optimum row length. And in general, in standard cell based design, we said that unequal rows are undesirable. So because it is often can produce some waste area, and it induce some uneven wear distribution. So this gamma 3 or the cos 3 basically actually penalize on the unequal row length. So gamma 3 is defined as the sum of the sum of the row length deviation from all the rows. Okay. Okay, so this is the way the cos tree has been defined. So it is again is a penalty of the penalty for the row inequality in standard cell based design. Okay, so so and this gamma 3 is again the priority weight of the cos tree. Okay. Now the next thing is that now let's look at the temperature reduction process in TimberWolf. Now, as you know, in simulated annealing, the temperature reduced by cooling factor. Okay, so you know that temperature is reduced in each iterations that, and the temperature is reduced by cooling factor alpha that we use. Okay, and now in TimberWolf, this temperature reduction schedule, we use a schedule function t, and that is somewhat, this schedule function is somewhat different from the normal simulated annealing algorithm whatever you have used so far in the floor planning or in partitioning. That is because in this alpha is basically, it's not a constant, rather than it is throughout the temperature range. So alpha is not constant throughout the temperature range, and so it's basically, it is a function of temperature also. Okay, so say, let's say this initial temperature or initial parameter value, the initial value of the parameter t is at very high, that is, let's say it is 4 into 10 to the power 6. Okay, and initially the temperature is also and this alpha t basically, so schedule t is alpha t into t, and this alpha t specifies the cooling rate which depends on the current temperature. So initially the temperature is reduced very quickly, and so alpha is usually taken as 0.8, and after a certain number of iterations the temperature reduces at a slower rate, so alpha t is 0.95 and in the medium range of the temperature. And finally towards the end the temperature is again reduced at the first phase, that is alpha equal to 0.8. Okay, so TimberWolf and finishes TimberWolf finishes when the t is less than t minimum, and t minimum is really, you can take it as 1. Okay. Now now this is the way actually the temperature reduction takes place, and it is in TimberWolf placement problem. Okay, and okay, now this is the whatever I have discussed as this cooling schedule of TimberWolf has been depicted through this diagram. So you can understand that initially it is decreases very fast, then there is a 0.95 cooling rate was used, then again 0.8 cooling rate was used. So you can get this kind of a profile when if I plot the temperature versus the number of iterations. This kind of profile I'm going to observe. Okay. Now the last thing is the number, how many times, means number of times through the inner loop. So what would be the how many times you have to do the iteration. So and each temperature, so at each temperature in number of cells are made to part up to generate the new placement, right? So at each temperature a fixed number of moves are attempted, and usually this optimal number of moves depends on the size of the circuit. And experimentally there is an instance of from that paper that is originally in TimberWolf paper, they have shown that for instance if we have a 2-cell circuit, okay, if we have a 2-cell circuit, then 100 moves per cells are recommended, and which calls for the evolution of 2.34 into 10 to the power 6 configurations, or total those number of moves are required in about 125 temperature steps. So this is experimental data, and based on your design style, this number of this number of times, how many times you have to Actually the number of times the inner loop has to be iterated. I mean, number of trials, how many number of trials you have to use for the inner loop iterations, that depends on the size of the circuit, and that is a hyperparameter also. Just like your alpha and your initial temperature, your final temperature, this things is also a kind of a hyperparameter, and you have to tune it based on your designs, okay, and experimentally you have to tune it, okay. So in summary of this TimberWolf, we can say that this placement is basically, placement problem is a combinatorial optimization problem. It is an NP complete problem, and we can use some heuristic algorithms like the simulated annealing to find out the near optimal solutions. And the TimberWolf is a simulated annealing based algorithm to solve this problems, this placement problem in standard cell based design. Okay. So with this, I am going to end this video, and we'll look at the force directed we'll look at the force directed approach for placement in the second part of this video. So with this, I'm going to stop this video. Thank you for watching.